Relation between Hurwitz zeta and polygamma function. First of all, let me define these two terms, Hurwitz zeta and polygamma function, if you are not familiar with this. So this is basically the Hurwitz zeta function, and this is defined as Hurwitz zeta of s comma a is defined as sum going from n equals to 0 to infinity 1 by n plus a to the power s. So this is basically the Hurwitz zeta function, and if a is 1, basically the Riemann zeta of Hurwitz zeta of s comma 1 is our normal zeta function. Okay, and now that is all about Hurwitz zeta that you need to know. And now let's go to polygamma function. So basically we have digamma function. Digamma function of 1 plus x is equals to minus solar mass constant plus sum from n equals to 1 to infinity 1 by n minus 1 by n plus x. Now basically the first derivative of digamma function, this is known as trigamma function, we can write it over here. The second derivative of digamma function is known as quadratic gamma function, and if you again differentiate this thing, you get digamma to the base 3 of x. So basically if you differentiate digamma to the base n of x, you get digamma n plus 1 of x, and this digamma base n of x, this is known as the polygamma function. Okay, and this is defined from this functional equation for all n's, and for 1, for let's say for 0, this one, okay, this one is for 1, and for 0 this is defined from this equation itself. Okay, so now let's move on to proving this theorem. But before we go, I would like to mention something. Fine. This is called digamma 0. And now to prove this, we go with basically the definition of digamma function itself, and then we will try to get this expression. At last I will show you how. So first of all, we know that digamma of 1 plus x, this is defined as negative upper mass constant, plus sum going from n equals to 1 to infinity 1 by n minus 1 by n plus x. Now if you try to differentiate this, we get digamma 1 of x plus 1. This is just constant with respect to x. Okay, remember that this is just constant, this is also constant. So we have sum from n equals to 1 to infinity, and then over here it is 1 by n plus x whole square. So this is Hurwitz zeta of basically, okay, wait a second, we can change this as, now we can change this too. We can write this as trigamma of x plus 1 is equals to sum going from n equals to 0 to infinity of 1 by n plus 1 plus x square. Now x plus 1, we replace that by x now. So we have trigamma of x is just sum going from n equals to 0 to infinity of 1 by n plus x whole square. Now this is a nice form, and we know that this is just Hurwitz zeta of basically x. Sorry, I think we need to start with s. S and then a. This is basically 2 comma x. Now if we differentiate this, what do you get? Polygamma base 2 of x, you can just differentiate this, and you will get minus 2 times sum from n equals to 0 to infinity 1 by n plus x whole cube. Yeah, that means you get minus 2 times Hurwitz zeta of 3 comma x. Okay, if you again differentiate the polygamma base 2, you get polygamma base 3, and this is now okay, so 6 times sum from n equals to 0 to infinity 1 by n plus x to the power 4. Now this is 6 times always zeta of 4 comma x. Now you can probably guess the next polygamma function base 4. This will just be minus 24 polygamma of 5 comma x. So I think you can clearly see clearly notice a pattern that we can make now. So if we have a polygamma base n of x, yeah, for odd there's no minus 1, for even there is, so that means we can write this as minus 1 to the power n plus 1. Yeah, so that it vanishes for odd numbers. And then here's the factorial of this same base, so n factorial, and then Hurwitz zeta of this is just n plus 1 times x. Okay, so we have got this expression. Now the thing that we need to prove is slightly different. Yeah, so for that we can take, let us first write this and I will let you know how to derive this. So we have achieved this expression, digamma n of x equals to minus 1 to the power n plus 1, and then n factorial, the Riemann zeta, sorry, Hurwitz zeta of n plus 1 comma what the x. Yeah, okay, so now if you have to convert this to this thing, you can replace n plus 1 by s. Yeah, and that gives us Riemann zeta of s comma x is equal to, now this will just be s minus 1. So polygamma base x, s minus 1 x by, now this is just s only, and this is s minus 1 factorial. So you see that we have just proved this expression. Yeah, and now we have these two formulas in hand, and we can use this to derive some more formulas, such as if you want to find digamma of 2n minus 1 x, we will get basically minus 1, and over here let's say it's 1. Yeah, minus 1 to the power, now 2n minus 1 plus 1 is just 2n, and then 2n minus 1 factorial, and then Riemann zeta of, so 2n comma 1, and this is just 7 zeta of 2n. Now we also have another expression for Riemann zeta of 2n. Yeah, now this is just 1, no need to write because we have even powers, and this is 2n minus 1 factorial. Now this is Bernoulli of 2n by 2n factorial. Yeah, and then minus 1 to the power n minus 1, sorry, n minus 1, 2 to the power 2n minus 1. Yeah, and then pi to the power 2n. Using this expression we can now get another formula, that is minus 1 to the power n minus 1, 2 to the power 2n minus 1, pi to the power 2n by 2. Okay, so I missed the Bernoulli number, also Bernoulli of 2n. Okay, so let me check if this is the formula or not. Minus 1 to the power n minus 1, 2 to the power 2n minus 1. Oh, by the way, I can take this 2 to the numerator, and okay, so basically 2n remains here. Yeah, if this cancellation occurs, 2n remains. I can take this 2 to over here in the power, cancel this and write 2n minus 2. Yeah, okay, 2 to the power 2n minus 2, pi to the power 2n, and by n. Now this is the correct formula for diagram of 2n minus 1. Okay, similarly if you have to find other values, like if you have to find digamma 1 of 1, you can use this formula, or you can also use this one also. So basically you will have -1 squared and then 1 factorial and then Riemann zeta of 2 comma 1 is Riemann zeta of 2. So this is just pi square by 6 itself. If you want to find digamma 3 of 1, this is also -1 to the power 4 and then 3 factorial and then Riemann zeta of 4. Yeah, this is just 6 times pi to the power 4 by 90. This is pi to the power 4 by 15. Yeah, so in this way their relation is helpful to compute some of the digamma values. Yeah, and this is also helpful in the summations that are in the form of this Hurwitz sum. At that cases we can take it to polygamma function and use some properties like reflection formula or something like that, and so it can be useful in such cases as well. So finally, hope you got the proof of the relation and some of the formulas and how to use those formulas to find polygamma values. And yeah, this was it. Thanks for watching. Look forward to seeing you in the upcoming videos too.